ELEC2 2019 question 8. Part A. The following circuit diagram shows a dedicated 4-bit synchronous ripple counter. Now you've met ripple counters in the past for up counters and down counters using D types, but this is obviously a chip to represent or a box to represent the counter. For part 1, distinguish between asynchronous ripple counters and synchronous counters. Well, this was actually very poorly answered nationally when this exam came up, but there are some set definitions. First one for a synchronous counter is where all stages are clocked at the same time due to the clock pulse. You think of synchronous counters that you did probably at the beginning of year 13. Okay, what about asynchronous counters? Asynchronous counters are the ripple counters, the D-type counters. And hopefully you realise that the clock isn't attached to every single one of the clocked inputs for the D-types. It's invariably the Q or the not Q, which is linked to the next clock. So, stages are clocked at different times by the output of the previous stage. And that output can be Q or not Q. Okay, for part 2. The counter is falling edge triggered and is initially reset. So falling edge being a key word here. Complete the timing diagram to show the effect of the subsequent 6 clock pulses on counter outputs B and A. So we know that this is an up counter and it's falling edge triggered. So it's a bit like your 4D type up counting type of configuration and the associated graphical output that you'd expect from that. So we're going to start initially low for A, and it's going to go high on the first of the falling edges, and it's going to stay high until we have the next falling edge. And you're going to get a repeating output based on those falling edges. Now B is dependent on the falling edge of the next input, and that input comes from A. So B will stay low until we get to the falling edge of A, then go high, stay high until the next falling edge of A, and basically then stay low until, and it will go high again on that last falling edge. Right, part B. The system based on a dedicated 4-bit counter and combinational logic is required to produce the following light sequence, and we've got our picture showing our light sequence with 4 separate stages. And we've shown that when it's grey the LED is on, and when it's black the LED is off. And we're asked to design the system by completing 3 things. The truth table, so the truth table comes from the picture. The Boolean expressions for the outputs X, Y and Z. Now that's going to come from the truth table. And the circuit diagram for this system. And we've been given the route as far as that circuit diagram is concerned, and we've got to add the logic to it connected to the outputs. Okay, so for the truth table, we've been given the first line. And what we need to realize is that our counter, and we can see it's a counter because we can look at the bottom, we've got a pulse generator into a counter, is basically going to count up in binary. So we can do C, B and A quite quickly because what we have is just a increasing binary number up to 1, 0, 0 or 4. Now what we need to do is we've been given the first line where all of the LEDs are off. So what is the second line? Well, we can look at the picture, and for row 2 we've got off, off, on. And for row 3, we've got off, on, off. Row 4, on, off, off. And then I suppose the mistake that probably students made when they were doing this is we need to realise that on the next number for the binary input, it cycles back to row 1. So it's 0, 0, 0. Right, okay, so for the Boolean expressions, the first thing for us to realise is for all 3 of these Boolean expressions, C doesn't matter. There are no high outputs where C is high. So those first 4 lines of the truth table, C is low for every single one, and therefore we can disregard it in that respect. Okay, so for X, what are the conditions where X is high? Well, hopefully you can see just by looking at the table that it's when B is high and A is high, so it's B and A. And we're going to do this by inspection because it's quicker. What about for Y? Well, for Y, the conditions, if we forget about C because C has no impact on anything, then B is high and A is low. So B and not A. And then for Z, it's B is low and A is high. So it's going to be not B and A. Now we've got to draw the circuit diagram based on those particular Boolean expressions. All right, so X is B and A. So what we're going to need to do is draw in an AND gate here for X, and then link that to B and A. And what we're going to do is just draw some lines going straight up for B and A, and then I'm just going to link those 2 lines to the AND gate, which is linked to X. Okay, for Y. Now for Y, A is it's B and not A. So we've got an AND gate again, but what we're going to need to do is stick in a NOT gate for one of those inputs, and that is going to be linked to A, whereas B is connected directly to the AND gate. And for Z, it's the other way around. We've got a AND gate again, we've got a NOT gate again, linked to our AND gate, but that NOT gate is linked to B, and A is connected directly. We finally need to sort out the reset, because as you can see in the diagram, it's been left floating. And to do this particular part, we need to go back to the truth table. And the truth table, if you remember, the very last line of the truth table, C went high and everything else was low. So the easiest connection to make as far as the reset's concerned is to link C to that reset. And that concludes question 8.